Welcome to Dream to Space. Tonight we travel outward, through the planets, past the edge of the Sun's reach, across the Milky Way and the galaxies beyond it, all the way to the oldest light in the observable universe. Find somewhere comfortable, let the science carry you. If this is the kind of journey you'd like to make again, a like and subscribe helps the channel grow. Now, let's begin the journey. Look straight up tonight, anywhere on Earth, and the light hitting your eye left its source at wildly different times. Some of it left the moon just over a second ago. Some left the sun 8 minutes ago. Some left a star on the far side of the galaxy 26,000 years ago. And some of it, the faintest and oldest light there is, left its source before the Earth existed, before the sun existed, before there were any stars at all to name. That light is still arriving. It has been arriving, steadily, for the entire history of the universe, and it defines the outer wall of everything we are able to see. Every point in space has its own observable horizon, its own sphere, centered on wherever it happens to be standing. An observer in a galaxy 4 billion light-years away has a horizon that overlaps with ours substantially, but is not identical to it. There is no single observable universe shared by all observers everywhere. There are as many observable universes as there are places to observe from. The size of that sphere deserves to be built, rather than simply stated. Light from the moon takes a little over a second to reach Earth. Light from the sun takes about 8 minutes. Light from the nearest star beyond our own sun, Proxima Centauri, takes just over 4 years. Already, at 4 light-years, ordinary intuition starts to strain, since nothing in daily human experience moves or is reached on a timescale like that. Climb further. Light from the center of our galaxy takes about 26,000 years. Light from the nearest large galaxy beyond our own, Andromeda, takes 2.5 million years. And the most distant light we can detect, light that has been traveling since almost the very beginning of time itself, has been redshifted and stretched by the universe's own expansion until the object that emitted it, were it still there today, would now be roughly 46 billion light-years away in every direction. Double that for the full sphere, and the figure is 93 billion light-years across. The observable universe is not 93 billion light-years old. It is 93 billion light-years wide, a span built by 13.8 billion years of light travel, combined with continuous cosmic expansion, stretching that light's path the entire time it traveled. This is the first and most important distinction this journey will rely on. The observable universe is not the same thing as the universe as a whole. The total universe may be far larger than what we can see, possibly even infinite. We have no way to measure its true size, because we have no way to receive any signal from beyond our own horizon. The boundary we are describing is not a wall in space, the way a coastline is a wall against the sea. It is a boundary in information. Beyond it, light simply has not had enough time to reach us yet, even traveling at the fastest speed permitted by physics. 2 principles make this boundary possible to define with any precision at all. The first is the finite speed of light, a hard ceiling on how fast any signal, any information, any influence can travel through space. The second is the age of the universe itself, 13.8 billion years, measured independently through multiple methods that will be covered later in this journey. Combine a fixed speed limit with a fixed amount of elapsed time, and the result is a fixed maximum distance any signal could have traveled to reach us. That maximum distance, adjusted for the fact that space itself has been expanding the entire time light was in transit, is what defines the edge of the observable universe. Underlying all of this is a working assumption astronomers call the cosmological principle. On the largest scales, the universe is broadly homogeneous and isotropic, meaning it looks roughly the same in every direction and from every location. Once you average out the lumpiness of individual galaxies and clusters, this is not a guess. It is supported by large-scale surveys showing that the distribution of galaxies however clustered locally, evens out into a consistent density when measured across sufficiently large volumes. The cosmological principle is what allows astronomers to assume that the laws of physics observed from Earth apply equally well everywhere else. Without it, there would be no basis for inferring anything about regions of the universe we will never visit. One consequence of all this shapes everything that follows. Because light takes time to travel, looking outward into space and looking backward into time are the same act. A telescope pointed at a galaxy 2 billion light-years away is not showing that galaxy as it exists now. It is showing that galaxy as it existed 2 billion years ago, before its light began the long crossing to Earth. The deeper this journey travels into the observable universe, the further back in cosmic history it simultaneously travels. Distance and look-back time are, from this point forward, two descriptions of the same measurement. To hold the scale of that look-back time in mind, it helps to compress the entire 13.8 billion year history of the universe into a single calendar year. If the Big Bang occurred at the first instant of January 1st, and this moment falls at the final instant of December 31st, then the Sun and Earth do not form until late August. The first complex animal life on Earth appears in mid-December. Dinosaurs go extinct on the morning of December 30th. All of recorded human civilization, every empire, every war, every book ever written, fits into the last few seconds before midnight on December 31st. And yet the light arriving at the very edge of what we can see tonight left its source in the first fraction of a second of that same January 1st, before stars, before galaxies, before atoms had even finished forming. We are, every clear night, looking at January and December at the same time. This journey will move outward from Earth in careful stages, each one marking a different kind of edge. Some edges are physical, the boundary of the Sun's gravitational influence, the rim of our galaxy's disk. Some are structural, the outer reach of the cluster of galaxies bound to our own. Some are observational, the furthest distance our instruments can currently resolve. And one, right at the limit of this entire journey, is a genuine wall, not in space, but in light itself, a point before which no photon could travel freely at all. Each threshold will be measured in 2 units simultaneously, how far away it is, and how long ago, in look-back time, the light we are seeing actually left. The destination of this journey is not a place. It is a horizon, one that every observer everywhere carries with them, expanding by roughly 1 light-year for every year that passes, not because we are exploring further outward, but simply because there has been more time for light to arrive. Understanding that distinction between a boundary in space and a boundary in available information is the foundation everything that follows will be built on. Leave Earth's orbit behind, and the first thing that changes is the silence of the gap. The sky, which from Earth's surface holds the Sun as an overwhelming presence, begins to shift. Mars sits roughly 1.5 astronomical units from the Sun, 1 astronomical unit being the Earth-Sun distance itself, and from its surface the Sun has already visibly shrunk, still the brightest object in the sky, but no longer the force that fills it. The journey between the two worlds takes a spacecraft the better part of a year, even on an efficient trajectory. Beyond Mars, the solar system does not get more crowded. It gets emptier. Between Mars and Jupiter lies the asteroid belt, a region millions of kilometers wide, popularly imagined as a dense field of tumbling rock, the kind of obstacle course depicted in science fiction. The reality is closer to nothing at all. The combined mass of every object in the asteroid belt is roughly 3 to 4% of the Moon's mass, scattered across so vast a volume that NASA's own missions have flown through it without a single planned course correction to avoid debris. This is not a wall. It is a debris field so sparse that calling it a belt slightly overstates its density. The objects within it, ranging from dwarf planet series at nearly 1,000 kilometers across down to gravel, are remnants of planet formation, material that Jupiter's gravity disrupted before it could accrete into a single world. That disruptive gravity becomes the dominant force of the next leg of the journey. Jupiter, at roughly 5.2 astronomical units, is so massive that it shapes the trajectory of nearly everything that passes near it. Its gravitational field has been used deliberately by mission planners as a slingshot. A spacecraft approaching Jupiter at the right angle can steal a small fraction of the planet's own orbital momentum and leave the encounter with significantly more velocity than it arrived with, all without burning a single drop of additional fuel. The physics are the same that let a moving train add speed to a ball thrown forward from inside it. Every probe that has ever reached the outer solar system, Pioneer, Voyager, Galileo, Cassini, New Horizons, has used this technique, often at Jupiter, sometimes chained through Saturn as well, to reach speeds that direct propulsion alone could never economically achieve. Saturn itself sits at roughly 9.5 astronomical units, its rings visible even through a modest backyard telescope from Earth. It is worth pausing on that image for a moment, someone in a garden on a clear night, eye to a small eyepiece, and the rings simply there, tilted and real and bright. Not everything in this outward journey is faint or theoretical. Some of it is bright enough to see with equipment a hobbyist owns. Past Saturn, the solar system continues to thin. Uranus sits at 19 astronomical units, a pale blue-green disk, its axis tilted so far from vertical that it orbits the Sun essentially on its side, rolling rather than spinning the way the inner planets do. From its cloud tops, the Sun is already so distant that it appears not as the broad, warm presence it is from Earth, but as an extremely bright star, still outshining everything else in the sky, but reduced to a point of light rather than a disk. A radio signal sent from Uranus takes nearly 3 hours to reach Earth at the speed of light. Neptune, the outermost of the 8 planets, sits at 30 astronomical units, and from its surface the Sun shrinks further still, a brilliant pinpoint in an otherwise dark sky, delivering less than 1,000th of the light and warmth it provides on Earth. A signal from Neptune takes over 4 hours to arrive. Both worlds were visited only once, by Voyager 2 on its long outward journey in the 1980s, and no spacecraft has returned to either since. Past Neptune, the character of the solar system changes again. This is where the traditionally mapped solar system reaches what was once considered its formal edge, a region named the Kuiper Belt. To understand the scale of this region, it helps to climb toward it gradually. A walk across a typical city block covers perhaps 1/10 of a mile. The distance from London to Edinburgh, a journey of several hours by car, covers roughly 400 miles. Scale that up by 1,000, and you approach the distance across the continental United States. Scale up by 1,000 again, and you are well past the distance to the Moon, 250,000 miles away. The distance from the Sun to Neptune, by contrast, is roughly 2.8 billion miles, and the Kuiper Belt extends from there, beginning around 30 astronomical units and reaching out to roughly 50, a vast disk of icy bodies, comets, and dwarf planets including Pluto, encircling the solar system like a debris ring left over from its formation, far larger and far more populated than the asteroid belt closer to home. For most of the 20th century, Pluto was the limit of direct human knowledge of this region. A single faint point of light discovered in 1930 by Clyde Tombaugh through painstaking comparison of photographic plates. Everything beyond remained theoretical, inferred from orbital dynamics and the gravitational tugs of unseen material, until a single spacecraft changed that directly. NASA's New Horizons probe, launched in January 2006, reached Pluto in July 2015 after a 9-year transit, performing the first close flyby of the dwarf planet and its moon Charon. The images returned were not blurred points of light. They showed a world with nitrogen ice plains, mountain ranges of water ice, and a thin, layered atmosphere, the first direct observational confirmation of what this region actually contained, rather than what models predicted it should contain. New Horizons did not stop there. In January 2019, after a further course adjustment, it performed a second flyby, this time of a much smaller and more distant Kuiper Belt object named Arakoth, a contact binary formed from 2 lobes that had gently merged in the early solar system. Arakoth remains the most distant object ever explored at close range by any spacecraft, and its preserved, Undisturbed structure offered direct evidence about the conditions under which the solar system's smallest building blocks first came together. Material essentially unchanged since formation 4.6 billion years ago. It is tempting, having reached the outer edge of this icy disk, to treat the Kuiper Belt as the true boundary of the Sun's domain. The evidence says otherwise. The Sun's gravitational pull does not stop at 50 astronomical units, and neither does the outward pressure of the solar wind, the continuous stream of charged particles flowing from the Sun's corona. Both extend dramatically further, into a region no spacecraft had directly sampled until Voyager 1, the probe that first slingshotted past Jupiter and Saturn decades earlier, finally crossed it. The Kuiper Belt marks the edge of the traditionally mapped planetary system. What lies beyond it is something else entirely, and that is where this journey turns next. Space at this distance is not empty in the way a room is empty. It is a medium, thin and invisible, but measurable, a flow of charged particles streaming outward from the Sun at speeds that would cross the continental United States in a fraction of a second, filling the space between the planets and pressing outward in every direction against whatever lies beyond. A spacecraft traveling through it registers nothing a human body would notice, but the instruments notice. Voyager 1, the same probe whose Jupiter and Saturn flybys made every subsequent outer system mission possible, had by this point travelled far beyond the Kuiper Belt covered in the previous chapter. On the 25th of August, 2012, after 35 years of continuous travel, one of its instruments recorded a change in its surroundings that none of its operators on Earth would fully understand for over a year. The boundary Voyager was approaching had no visible marker, no surface, nothing a camera could photograph. It was the heliopause, the point where the outward pressure of the Sun's solar wind finally drops to match the pressure of the thin, cold material drifting between the stars. The solar wind itself is a continuous outflow of charged particles, mostly protons and electrons, streaming from the Sun's outer atmosphere at speeds often exceeding 1,000,000 miles per hour. This stream inflates a vast bubble around the entire solar system, a region called the heliosphere, within which the Sun's particles and magnetic field dominate the local environment. Beyond the heliosphere lies the interstellar medium, the diffuse material, far colder and far less energetic, that fills the space between star systems throughout the galaxy. Where these two pressures balance is the heliopause, sitting on average at roughly 120 astronomical units from the Sun. To place that figure against something climbable, begin with Neptune, 30 astronomical units out, already a distance that took Voyager 212 years to reach after launch. The Kuiper Belt extends from there out to roughly 50 astronomical units. The heliopause lies more than twice as far again past the Kuiper Belt's outer edge, at 120 astronomical units, a boundary so distant that sunlight itself, travelling at the fastest speed physics allows, takes over 16 hours to cross from the Sun to that threshold. Voyager 1 could not see this boundary coming. What changed in the weeks around that August date was the density and behaviour of the plasma surrounding the spacecraft. The instrument capable of detecting it was the Plasma Wave Subsystem, designed to measure the density of charged particles by listening to the natural oscillations that those particles produce. As Voyager 1 crossed from the hot, sparse plasma of the outer heliosphere into the colder, denser plasma of true interstellar space, the instrument recorded a sudden jump in electron density of roughly 20-fold, comparable in proportion to the difference between a light drizzle and standing rain measured by the same gauge, a sharp and unambiguous signature with no equivalent anywhere closer to the Sun. That signature alone would not have settled the question. The data did not return a clean answer until April 2013, when a naturally occurring solar event sent a shockwave outward from the Sun, reaching Voyager's position more than a year after it had already crossed the boundary, and causing the surrounding plasma to oscillate strongly enough for the instrument to measure its density directly. That delayed measurement confirmed what the original density jump had suggested. Voyager 1 was no longer surrounded by solar wind plasma. It was surrounded by interstellar plasma. By that combined evidence, NASA confirmed that Voyager 1 had become the first human-made object to cross into interstellar space, an event now dated to that initial boundary crossing in August 2012, even though final confirmation arrived nearly a year afterward. This is worth pausing on, because it demonstrates something this journey will return to. A single instrument reading, however dramatic, is rarely treated as proof on its own. It took two separate plasma density measurements, taken more than a year apart and triggered by entirely different events, agreeing with each other, before the crossing was considered scientifically confirmed. To hold Voyager's position against the scale of what surrounds it, consider that it has been travelling continuously for over 35 years at more than 38,000 miles per hour, a speed that would cross the continental United States in under 5 minutes. At that pace, it has reached 120 astronomical units from the Sun, and yet the interstellar space it now moves through is not the empty void it might appear from a distance. The interstellar medium has its own structure, its own temperature, its own density of particles, however thin. It carries magnetic field lines threading through the galaxy over distances that dwarf anything the heliosphere contains. Voyager's instruments, still functioning after decades of travel, continue to sample this environment directly, sending back data about a region of space no human instrument had ever reached before. A slow and patient form of exploration conducted entirely by a machine the size of a small car, coasting now on the momentum of a launch that happened nearly half a century ago. The Oort cloud lies far beyond even this. A vast and only indirectly observed shell of icy bodies thought to surround the entire solar system. It is theorized to extend outward to somewhere in the range of 100,000 astronomical units, nearly 1,000 times farther than the heliopause itself. The objects within it are believed to be the source of long-period comets that occasionally fall inward toward the Sun after gravitational nudges from passing stars or the gentle tidal pull of the galaxy itself, arriving in the inner solar system after journeys of millions of years from a reservoir so distant that no spacecraft has come remotely close to it, and none currently planned will reach it within any human timescale. The Oort cloud has never been directly observed. Its existence is inferred entirely from the behavior of the comets it sends inward, the way the presence of a distant shore can be inferred from the waves it sends back, without ever seeing the shore itself. The Sun's gravity, unlike its wind and its magnetic field, has no sharp boundary. It simply fades, gradually, until it is overtaken by the combined pull of every other star in the galaxy. And somewhere out there, still transmitting, still measuring, Voyager continues into that dark, the furthest thing humanity has ever placed in the universe, not yet close to gone. On a clear night, far from artificial light, the Milky Way appears as a pale band stretching across the sky, soft and motionless. The way a long-exposure photograph of traffic on a distant motorway can look like a smear of solid light, rather than thousands of separate moving cars. That stillness is an illusion of distance, and it is worth holding on to, because the natural instinct, looking at a band of light like that, is to treat the galaxy as a fixed structure, a map that simply exists, fully formed, the way a country exists on a printed atlas. That instinct is wrong in a specific and important way. The Milky Way is a barred spiral galaxy, a flattened disk of stars, gas, and dust, roughly 100,000 light-years across, with spiral arms winding outward from a dense central bulge, their shape maintained by the gravitational dynamics of the galaxy's own rotation. The Sun sits within one of these arms, a minor structure named the Orion Arm, located roughly 26,000 light-years from the galactic center, the same distance, noted in the opening chapter of this journey, that the galactic center's light takes to reach us. Stated as a static map, this sounds like geography. It is not geography. It is history, layered and frozen at different depths depending on how far away each point of light happens to be, and unpacking that distinction is the real subject of this stage of the journey. Determining these distances at all required astronomers to solve a problem that, for most of human history, had no solution. There is no ruler long enough to lay across a galaxy. The first reliable method came from a class of star called the Cepheid variable, identified in the early 20th century through the work of astronomer Henrietta Leavitt. Cepheids pulse in brightness with a regular period, and Leavitt discovered that the length of that pulse period correlates directly and predictably with the star's true intrinsic brightness. That relationship turns Cepheids into what astronomers call standard candles. Measure how long a Cepheid takes to pulse, and its true brightness is known. Compare that true brightness to how dim it actually appears from Earth, and the difference reveals the distance, since light fades in a precise, calculable way over distance. This single technique, refined over decades, allowed astronomers to begin mapping not just the rough shape of the galaxy, but specific distances within it, including the distance from the Sun to the galactic center. Cepheid measurements carried this work for most of the 20th century, but they have real limits. They require finding individual pulsing stars bright enough to detect and rare enough that their pulse periods can be cleanly measured, a patchy and labor-intensive process. The breakthrough that transformed galactic mapping into something approaching precision came from a spacecraft, not a single star type. The European Space Agency's Gaia mission, launched in 2013, uses parallax, the same basic geometric principle that lets a person judge distance by holding a finger at arm's length and watching it shift against the background when alternating which eye is open, except Gaia uses the width of Earth's orbit around the Sun as its baseline rather than the distance between two eyes. By measuring the tiny apparent shift in a star's position as Earth moves from one side of its orbit to the other, Gaia calculates distance directly and geometrically, without relying on any assumption about a star's intrinsic brightness at all. Gaia has applied this method to over 1 billion stars, producing the most precise three-dimensional map of the galaxy's structure ever assembled, and confirming, with far tighter error margins than Cepheid measurements alone could offer, both the galaxy's overall disk diameter and the Sun's specific position within it. To hold the scale that mapping revealed, begin with something walkable. A determined hiker can cross perhaps 20 miles in a day. Mainland Britain, end to end. From the southern coast of England to the northern tip of Scotland, spans roughly 600 miles, a multi-week trek on foot, an afternoon's drive by car. Now imagine the entire Milky Way, all 100,000 light-years of it, shrunk down to fit precisely onto that same island, end to end. On that scale, the solar system, including the Kuiper Belt, and even the outer reaches of the heliopause covered earlier in this journey, would not register as a town, or a building, or even a coin dropped on the ground. It would be smaller than a single grain of sand, lost somewhere along that 600-mile span, indistinguishable from the millions of other grains representing every other star system in the galactic disk. This is where the static map instinct breaks down completely. The light reaching Earth from the galactic center left that region roughly 26,000 years ago, before agriculture, before the first cities, well into the depths of the last ice age. Every photograph, every observation, every map of the galactic center is necessarily a photograph of how that region appeared 26,000 years in the past, not as it exists now. This is not a small caveat. It means that no human being, with any instrument that has ever existed or will exist using light alone, can see the Milky Way as it currently is. We see a galaxy built entirely out of layered, mismatched moments frozen at the instant their light departed, some fragments only decades old, others tens of thousands of years stale, all arriving together and appearing, to the naked eye on a clear night, as a single still band of light. The pale, motionless arc overhead is not a snapshot. It is a composite of 10,000 different pasts, all arriving at once. On a dark autumn night, away from city light, a faint smudge is visible to the naked eye in the constellation Andromeda, easy to mistake for a wisp of cloud or a flaw in the eye itself. It is neither. It is an entire galaxy, 2.5 million light-years away, and it is moving toward us. That galaxy, Andromeda, also known by its catalogue designation M31, is the largest member of a small cluster of galaxies that includes the Milky Way, a gravitationally bound collection called the Local Group. The Local Group contains over 80 known galaxies, most of them small, faint dwarf systems easily overlooked, spanning a region roughly 10 million light-years across. Within that group, two galaxies dominate by mass and gravitational influence. The Milky Way, whose disk and position were mapped in the previous chapter, and Andromeda, somewhat larger still, the two of them orbiting a shared center of mass alongside their smaller satellite galaxies, the way two heavyweight bodies in a binary system orbit each other while smaller debris trails along. The distance to Andromeda was established using the same Cepheid technique covered in the previous chapter. Pulse period reveals true brightness, and true brightness compared against observed dimness reveals distance. Edwin Hubble used exactly this method in the 1920s, identifying individual Cepheids within Andromeda using the largest telescope then available, and calculating a distance far greater than the diameter of the Milky Way itself. That measurement was, at the time, genuinely controversial, since it settled a long-standing debate over whether objects like Andromeda were relatively nearby clouds of gas within our own galaxy, or entirely separate galaxies in their own right, external island universes spread across vastly greater distances. Hubble's Cepheid measurements resolved the question decisively. Andromeda was not part of the Milky Way. It was a second, comparably massive galaxy, 2.5 million light-years distant, and the universe was immediately understood to be far larger than previously assumed. Establishing the distance was only half the picture. The more striking property of Andromeda is not where it sits, but how it is moving, and that required an entirely different measurement technique, spectroscopy. When light from a star or galaxy passes through a prism or diffraction grating, it spreads into a spectrum marked with dark absorption lines, each corresponding to a specific wavelength absorbed by particular elements in the object's own atmosphere: hydrogen, helium, calcium, and others, each with a known, fixed wavelength measured precisely in laboratories on Earth. When the source of that light is moving away from an observer, those lines shift toward the red end of the spectrum, a phenomenon called redshift. And when the source is moving toward the observer, the same lines shift toward the blue end instead, a blue shift. The amount of that shift corresponds directly to the velocity of the motion, using the same physical principle that causes an ambulance siren to drop in pitch as it passes and recedes. When astronomers examined Andromeda's spectrum, the absorption lines were not shifted toward red. They were shifted toward blue. Andromeda is one of the relatively rare galaxies in the observable universe moving toward the Milky Way rather than away from it, and the size of that blue shift allows its closing radial velocity to be calculated with real precision, roughly 110 kilometers per second. Gaia's precise tracking has since confirmed a significant sideways component to that motion as well, meaning the full closing speed is somewhat higher, though the overall trajectory remains consistent with what spectroscopy first established. To place that velocity against something graspable, start with a fast highway speed, perhaps 70 miles an hour, around 30 meters per second. A commercial jet cruises near 250 meters per second. Climb further, past the speed of sound, beyond even the fastest fighter aircraft, and you approach the velocity of a rifle bullet leaving the barrel, often in the range of several hundred to over 1,000 meters per second depending on the round. Andromeda's radial closing speed translates to roughly 110,000 meters per second, and yet the room that speed is crossing is 2.5 million light-years long, a gap so vast that even at that pace, the two galaxies will not meet for approximately 4.5 billion years. This is not a speculative projection built on shaky assumptions. The trajectory is among the most confidently established large-scale predictions in galactic astronomy, supported by decades of consistent spectroscopic measurement, by Gaia's precise tracking of Andromeda's motion across the sky, and by detailed gravitational modeling of how the two galaxies' mass distributions will interact as they near each other. When the collision eventually occurs, individual stars within each galaxy are expected to pass by one another, largely undisturbed, since the distances between stars even within a galaxy's crowded disk are vast enough that direct collisions remain unlikely. The two galaxies' overall structures will be gravitationally reshaped over hundreds of millions of years into a single, larger elliptical galaxy, a merger some astronomers have already informally named Milkomeda. The local group, then, is not a static cluster of separate galaxies drifting independently through space. It is a gravitationally bound system already in the early stages of consolidation, and the forces driving that consolidation reach far beyond just these two galaxies, into a structure large enough that no single telescope has ever captured it in one frame. Imagine standing at the edge of a vast watershed, a landscape so large that no single viewpoint could take it in. Every stream, every river, every trickle of water across an enormous region flows toward the same distant basin. Not because anything is pushing it there, but simply because of the shape of the ground beneath it. The structure this chapter describes was found the same way, not by photographing it, but by watching which way everything within it was moving. The local group, the gravitationally bound cluster of more than 80 galaxies, including the Milky Way and Andromeda, is not an isolated structure drifting alone through space. It belongs to something far larger called the Virgo supercluster, a loose collection of galaxy clusters and groups spanning roughly 110 million light-years. The Virgo supercluster itself, a team of astronomers led by Brent Tully demonstrated in 2014, is merely one lobe of an even larger structure they named Laniakea. To place its scale against the Milky Way mapped earlier in this journey, where the entire 100,000 light-year galactic disk would be lost as a single grain of sand on a map of Britain, Laniakea is roughly 5,000 times wider still, a supercluster roughly 500 million light-years across, encompassing the Milky Way, Andromeda, the Virgo cluster, and approximately 100,000 other galaxies, all loosely bound by gravity into a single coherent system. Laniakea is not the kind of object that reveals itself through direct imaging. A structure that large cannot be photographed the way a single galaxy can, since its galaxies are scattered across such enormous distances that no instrument captures the whole shape in one frame. Tully's team built their map using a technique grounded in motion rather than position. Every galaxy in the universe has two components to its observed velocity. The first is the expansion of space itself, the Hubble Flow, a uniform outward recession affecting every sufficiently distant galaxy roughly in proportion to its distance, a concept this journey will explore in the next chapter. The second component is what astronomers call peculiar velocity, the galaxy's own additional motion through space, caused by the localized gravitational pull of nearby concentrations of mass, including the unseen dark matter that makes up most of any galaxy cluster's gravity, the same kind of pull that draws Andromeda toward the Milky Way, rather than simply receding with the general expansion. By carefully subtracting the expected expansion velocity from each galaxy's total observed velocity, using large surveys of galaxy redshifts and distances, Tully's team isolated those peculiar velocities for tens of thousands of galaxies across a vast volume of space. What emerged, once those individual peculiar motions were plotted together, was not random, scatter. It was flow. Galaxies across an enormous region were found to be moving, gradually and collectively, toward shared gravitational basins, regions of higher mass density pulling everything nearby toward them. Laniakea was defined not by any visible boundary but by a watershed, a continuous region within which every galaxy's peculiar motion flows toward the same central concentration of mass. In the same way, a geographic watershed is defined not by a fence, but by the simple fact that every drop of rain falling within it eventually flows to the same river. The discovery resolved something that had genuinely puzzled astronomers for years. The Milky Way had long been observed to be moving at a substantial velocity in a specific direction relative to the cosmic microwave background, but the precise gravitational source pulling it that way had remained only partially understood. Tully's flow mapping showed the Milky Way was not moving randomly. It was flowing, along with everything else in its supercluster, toward the gravitational center of Laniakea itself. But even Laniakea's own basin does not appear to be the final destination. The flow mapping that revealed Laniakea also showed something further out, a massive, gravitationally significant concentration of matter known, somewhat informally, as the Great Attractor. Located beyond Laniakea's own boundary and partially obscured from direct observation by the dense foreground of our own galaxy's disk, a region astronomers call the Zone of Avoidance. The Great Attractor's full nature remains genuinely unresolved. Its mass is inferred from the motion it induces in everything around it, not from direct imaging of the structure itself, and some researchers have proposed it may itself be drawn towards something larger still, a concentration sometimes referred to as the Shapley supercluster, lying even further beyond. Whether gravitationally organized structure in the universe has any true upper limit remains an open question. Beyond a certain scale, gravity itself stops being the dominant force shaping how galaxies move at all, and that is where this journey turns next. Picture a leaf dropped into a river, past the point where the banks still shape its path. It is no longer drifting toward anything. It is simply carried, steadily and without resistance, by the current itself. Somewhere beyond the gravitational basin that defines Laniakea, a galaxy moves the same way. Every threshold covered up to this point in the journey, the heliopause, the Milky Way's disk, the local group, Laniakea itself, has been organized by gravity, a force strong enough, at those scales, to bind objects together or draw them along shared flows toward common centers of mass. Beyond a certain distance, gravity loses that organizing power. The galaxies out there are receding from every other galaxy around them, uniformly, in every direction, and the cause is not motion through space at all. It is the expansion of space itself, a phenomenon astronomers call the Hubble Flow. In 1929, Edwin Hubble, the same astronomer whose Cepheid measurements established the true distance to Andromeda, compared the distances of a sample of galaxies against their redshifts, the same spectroscopic stretching of light used earlier in this journey to measure Andromeda's motion. The further away a galaxy was, the faster it appeared to be receding, and the relationship between the two was strikingly linear. Picture it as a rubber sheet with dots marked on it, stretched evenly from every direction at once. Two dots close together drift apart slowly. Two dots far apart on the same sheet drift apart faster, not because either one is moving independently, but because there is simply more stretched sheet between them. That is the Hubble flow, and the rate at which it proceeds is described by a single number called the Hubble constant, relating a galaxy's recession velocity directly to its distance. A megaparsec is roughly 3.26 million light-years, and the Hubble constant describes how fast 2 points that far apart are being carried away from each other by the expansion of space. It is not a speed any object is travelling through space. It is the rate at which space itself is stretching between them. To place that against something more immediate, consider two galaxies sitting 1 megaparsec apart today. Under the Hubble flow, the space between them is expanding at a rate of somewhere between 67 and 73 kilometers every second, depending on which measurement you trust. They are not moving through space the way a car moves down a road. The road itself is quietly lengthening beneath them, and they are simply along for the journey. Pinning down the precise value of that constant has occupied cosmologists for nearly a century, and in recent years it has produced one of the most genuinely contested disagreements in modern astronomy. There are two broad approaches to measuring it. The first builds what astronomers call the cosmic distance ladder, anchoring measurements locally using Cepheid variables of the kind covered earlier in this journey, then extending outward using exploding stars called Type Ia supernovae, whose consistent peak brightness makes them reliable standard candles at far greater distances than Cepheids alone can reach. Teams using this distance ladder method, including extensive work led by Adam Rees and collaborators, consistently arrive at a Hubble constant close to 73 kilometers per second per megaparsec. The second approach works entirely differently. It measures the Hubble constant indirectly by analyzing the tiny temperature fluctuations imprinted on the cosmic microwave background, the relic radiation from the early universe that a later chapter will examine in full. Using detailed physical models of how the early universe evolved, teams analyzing data from the Planck satellite calculate a Hubble constant from that early universe imprint of roughly 67 kilometers per second per megaparsec. Two methods. Two well-funded, carefully scrutinized research communities. Two different answers to the same question. Both figures come from rigorous, independently cross-checked work. Both research communities have spent years tightening their error margins, hunting for overlooked sources of bias, recalibrating their instruments and assumptions. The two values still do not agree, differing by a margin large enough, roughly 5 standard deviations by the statistical measure cosmologists use, that it cannot reasonably be dismissed as ordinary measurement noise. This is the Hubble tension, and as of the most recent published analyses, it remains unresolved. What makes the tension genuinely significant is not simply that two numbers disagree. It is that both methods are considered mature and well understood within their own frameworks. The distance ladder has been refined over decades, its rungs checked and rechecked by independent teams using independent instruments. The cosmic microwave background analysis rests on one of the most precisely measured datasets in all of science. If either method contained a simple overlooked error, it would likely have been found by now. The fact that the disagreement persists despite that scrutiny suggests one of two possibilities. Either there is a subtle systematic bias in one or both methods that has so far resisted detection, or the standard model of cosmology itself is missing something, some ingredient in the universe's history or composition that affects the two measurements differently. Neither possibility is comfortable. Both are actively being investigated. To hold what that disagreement means, imagine two highly competent survey teams independently measuring the exact same stretch of coastline. One team works from the shore inward, anchoring each measurement to the last using a chain of established landmarks, the way the distance ladder anchors each rung to the one below it. The other team works from above, using satellite triangulation and a physical model of the coastline's formation to calculate its length without ever walking it directly. The way the cosmic microwave background method calculates the Hubble constant from early universe physics rather than nearby objects. Both teams check their work repeatedly. Both report tight, confident margins of error, and when their final figures are compared, the lengths disagree by more than either team's stated uncertainty allows for. That is the situation cosmology finds itself in today. Set that unresolved disagreement aside for a moment, and step back far enough from any single galaxy caught in this expansion. A second discovery emerges, one about shape rather than speed. Large galaxy surveys, most prominently the Sloan Digital Sky Survey, which has charted the positions and redshifts of millions of galaxies since the early 2000s, reveal that galaxies receding under the Hubble Flow are not scattered randomly through space. They are arranged along filaments, thin threads of galaxies and dark matter stretching across hundreds of millions of light-years, which connect at denser nodes and enclose vast, nearly empty voids between them. Those voids are not small. Some span hundreds of millions of light-years across, regions of space so underdense that a traveler passing through one would see almost nothing in any direction for a distance that dwarfs the entire local group. The filaments threading between them contain the overwhelming majority of all the galaxies in the observable universe, clustered and tangled along structures that formed from the same tiny density fluctuations seeded in the earliest moments of cosmic history. This structure, named the cosmic web, is the largest connected structure the universe contains, and every galaxy carried outward under the Hubble flow, including all the uncertainty over exactly how fast that carrying proceeds, is strung along those same threads, moving apart from everything else, steadily and without resistance, the way a leaf moves with a river it can no longer leave. An ambulance approaches along a quiet street, siren rising in pitch as it nears, then drops noticeably the instant it passes and begins to pull away. Most people have heard this enough times to recognize it instantly, without ever needing to know its name. The siren's pitch did not actually change. The sound waves reaching the ear were compressed on approach and stretched on departure, and that stretching, read by the ear alone, is enough to judge that the ambulance is moving away, and roughly how fast. Light behaves the same way when its source is moving through space, a phenomenon called Doppler shift. When a light source moves toward an observer, its waves arrive compressed, shifted toward the blue end of the spectrum. When it moves away, those waves arrive stretched, shifted toward the red. It was exactly this principle, applied to light rather than sound, that revealed Andromeda's blue-shifted approach toward the Milky Way 2 chapters ago. The absorption lines in Andromeda's spectrum were not where they should have been. They had shifted, measurably and consistently, toward blue, and the size of that shift gave a precise closing velocity. The same tool, applied to galaxies moving away rather than toward us, reveals a redshift instead. And it was the accumulation of those redshifts across dozens of galaxies that first allowed Hubble to map the recession described in the previous chapter. But the redshift that defines the Hubble flow is not quite the same phenomenon as Doppler shift, and the distinction matters enough to address directly before going further. Doppler shift describes an object moving through space, the way a siren or a galaxy can physically travel from one location to another. Cosmological redshift describes something different. Light stretching not because its source is moving through space, but because the space the light is traveling through is itself expanding while the light is in transit. A photon leaves a distant galaxy at a certain wavelength, begins its journey toward Earth, and over the billions of years that journey can take, the universe expands around it, stretching the photon's wavelength along with the space it occupies. The way a wavy line drawn on a rubber band stretches and lengthens as the band itself is pulled wider, without the line ever moving relative to the rubber it is drawn on. By the time that light reaches a telescope on Earth, its wavelength has lengthened, shifted toward the red end of the spectrum, not because the source galaxy raced away through space, though at extreme distances it may also be doing that, but because the universe expanded beneath the light the entire time it traveled. Astronomers quantify this stretching using a single value, denoted Z, calculated by comparing a light source's observed wavelength against its original, laboratory-known wavelength. A redshift of Z equals 1 means the light's wavelength has stretched to double its original length, and at that specific value, the look-back time works out to roughly 7.7 billion years, placing the emitting galaxy at a moment when the universe was still considerably younger than it is now. Higher Z values correspond to greater stretching, greater distance, and earlier moments in cosmic history, making redshift simultaneously a distance indicator and a clock. Measuring that stretch precisely depends on having something fixed to measure it against. Atoms absorb and emit light only at very specific, fixed wavelengths, determined by the physics of their electron structure, the same physical constants everywhere in the universe. Hydrogen, the most abundant element in the cosmos, produces a particularly important marker called the Lyman alpha line, emitted or absorbed at a precise wavelength deep in the ultraviolet, measured to extraordinary precision in laboratories on Earth. When astronomers examine the spectrum of a distant galaxy or quasar, they search for this signature line among the object's spectrum. Find the Lyman alpha line sitting not at its native ultraviolet wavelength, but stretched out into visible light, or further still into infrared, and the degree of that stretch gives a precise, repeatable redshift value, since the line's original wavelength is a known constant, not an estimate. What makes this tool so powerful is not just its precision, but its universality. The physics governing which wavelengths hydrogen absorbs and emits are the same everywhere in the observable universe, because the fundamental constants of nature, the charge of an electron, the mass of a proton, the speed of light, are the same everywhere we have been able to test them. A hydrogen atom in a galaxy 10 billion light-years away absorbs and emits at exactly the same wavelengths as a hydrogen atom measured in a laboratory on Earth. That consistency is not assumed. It has been tested, repeatedly, across enormous distances and look-back times, and it holds. It is what makes the Lyman alpha line a reliable ruler rather than a convenient approximation. and it is what allows every redshift measurement in this journey to be treated as a genuine distance and age, rather than an educated guess. Picture a long corridor, dimly lit, stretching further than the eye can follow. At the near end, objects are close enough to measure with familiar tools, parallax, Cepheid variables, the methods covered earlier in this journey. Further along, those methods run out of reach. The corridor keeps going, but the familiar markers are gone. Redshift is what allows the journey to continue past that point, a single measurement that works at any distance, reading distance and age simultaneously from the stretching of a single known line. To climb toward how large a stretch this represents, begin with something simple. A piece of string stretched to 1.5 times its resting length, a small and easily noticed change. Stretch it to twice its length, and the change is obvious at a glance. Comparable to a redshift of z equals 1, light that left its source 7.7 billion years ago. Push further, to 3 times, then 10 times the original length. And the object producing that light departed when the universe itself was only a few 100 million years old. Deep in the era this journey will reach in the chapters ahead. This single tool, a known spectral line compared against its stretched, observed counterpart, is what makes everything still ahead in this journey legible. Every distance and every age cited from here forward is derived from this same measurement, not observed directly with a ruler, but read, the way a passing siren is read, from the stretching of a wave, held at arm's length. A single grain of sand covers roughly the same patch of sky that the Hubble Space Telescope once spent 10 consecutive nights staring at. A patch every existing survey and every visible inspection had written off as empty. The decision, in December 1995, was a contested one. Telescope time on Hubble was, and remains, an intensely competed resource, awarded only after rigorous review, and the proposal to dedicate 10 full nights to an apparently empty patch of darkness struck some astronomers as a poor use of that resource. Robert Williams, then director of the Space Telescope Science Institute, used his own discretionary time to authorize it anyway, betting that emptiness, at that resolution, was simply a failure of prior instruments rather than a true absence of anything to see. The target was chosen specifically because it was clear of bright foreground stars and known nearby structures that might have obscured a deeper view. Hubble captured the field across 342 separate exposures over those 10 days, each one accumulating faint light that no single shorter exposure could have gathered, then combined into a single image, far deeper than anything pointed at that patch before. What emerged, once the exposures were combined, was not emptiness. It was depth. Packed into that single grain of sand patch of sky were nearly 3,000 galaxies, of every shape and size, stacked behind one another, not as a flat field, but as a genuine cross-section through cosmic time itself. The redshift tool developed in the previous chapter revealed that the galaxies in the image were not all at the same distance. Some were relatively close, their light only modestly stretched. Others sat far deeper, their light redshifted dramatically, meaning it had departed billions of years earlier, when the universe itself was a small fraction of its current age. A single small patch of apparently empty sky had turned out to be a window stacked with galaxies spanning most of cosmic history, simply because Hubble had finally gathered enough light to detect objects too faint for any previous instrument to register at all. That original 1,995 deep field, followed by an even more sensitive ultra-deep field campaign in 2003 and 2004, pushed the detectable redshift frontier further than ever before, but a hard limit remained. Hubble observes primarily in visible and near-infrared light, and the most extremely redshifted galaxies, the ones whose light departed earliest in cosmic history, have had their emitted light stretched so far by cosmic expansion that it arrives at Earth not as visible light at all, but shifted entirely into infrared wavelengths. Hubble was never built to capture with full sensitivity. Reaching those earliest galaxies required a different instrument. The James Webb Space Telescope, launched in December 2021 and optimized specifically for infrared observation, was built in large part to push past exactly this limit. It has done so repeatedly. Among its early discoveries was a galaxy designated GN Z11, originally identified by Hubble and spectroscopically confirmed by JWST at a redshift beyond Z=10, placing its emitted light at under 500 million years after the Big Bang. JWST has continued pushing that frontier since. By 2026, the confirmed record had moved past Z=14, with a galaxy-designated MOM, Z14, representing the most distant spectroscopically confirmed source yet found, its light departing around 280 million years after the Big Bang. Given how rapidly this frontier has moved, it is likely to have shifted again by the time this is watched. Each of these galaxies is not just a faint smudge confirming that something existed that early. Each one is a measurement, redshift read directly from stretched light, distance and age following from that single number. The same tool built in the previous chapter doing exactly the job it was built for, at the very edge of what it can reach. What makes these discoveries scientifically significant is not simply that JWST found galaxies further away than Hubble could reach. It is what those galaxies look like once found. Existing models of early galaxy formation, built before JWST's launch, predicted that galaxies this early in cosmic history should be small, faint, loosely assembled clumps of young stars, barely beginning the long process of growing into anything resembling a mature galaxy. Several of the galaxies JWST identified at these extreme redshifts instead appeared unexpectedly massive and surprisingly structured, displaying organized features that prior models suggested should have taken much longer to assemble. This tension remains genuinely open and is actively debated within the astronomical community. Two explanations are currently being weighed against each other. The first is that early star formation simply proceeded faster than current models account for, perhaps through more efficient gas collapse in the dense, compact conditions of the early universe. The second is that the mass estimates themselves carry more uncertainty than first appreciated, since measuring the mass of a galaxy at the very edge of detectability is a far harder problem than measuring its redshift alone. Neither explanation has won out yet. What is not in dispute is the redshift measurements themselves. What remains unresolved is how galaxies that early in cosmic history grew as large and as structured as some now appear to be. JWST continues observing, and the answer, when it comes, will almost certainly require revising something in the current picture of how the earliest structures in the universe assembled themselves. For roughly the first 150 million years after the Big Bang, there was nothing to see. Not because nothing existed, but because the universe itself was opaque, a haze of neutral hydrogen gas thick enough that light could not travel through it freely in any direction. Picture a vast indoor stadium, completely filled with thick, even fog, dense enough that a light held at one end is invisible from the other. The air itself is the obstacle. Not distance, not darkness, but the sheer density of the medium between one point and another, absorbing and scattering everything before it can cross the space between. Now imagine floodlights switching on, not all at once, but scattered, one section at a time, each one slowly burning a clear patch through the fog immediately around it. Close to each light, the air clears. The structure of the stadium becomes visible in that small radius, the seats, the railings, the floor. But step back far enough and the cleared patches are still islands in a sea of haze, isolated and surrounded. For a long while the stadium remains mostly obscured, patches of clarity scattered among the fog. Eventually enough lights have switched on, and enough patches have merged and overlapped that the fog clears entirely, and the whole space becomes visible at once, not gradually from one end to the other, but in a network of expanding clearings that finally connect. That gradual clearing describes, with reasonable accuracy, one of the most significant transformations in the universe's early history, the Epoch of Reionization, a process that unfolded over a span lasting from roughly 150 million years after the Big Bang to approximately 1 billion years afterward. the period the previous chapter found JWST detecting structured galaxies already in place within. Before this epoch began, the universe was filled with neutral hydrogen gas, electrically uncharged atoms left over from an era this journey will reach in the next chapter, when protons and electrons first combined. Neutral hydrogen absorbs ultraviolet light extremely efficiently, which is why this period is often called the Cosmic Dark Ages. Dim and largely featureless, aside from the earliest faint glimmers of structure beginning to collapse under gravity within it. Those collapsing regions, overdense patches seeded by the tiny fluctuations this journey will find imprinted on the cosmic microwave background, are what eventually gave rise to the first stars. The process was slow by human standards, measured not in years or centuries but in tens of millions of years of gradual gravitational collapse, gas clouds growing denser, temperatures rising at their cores, until finally the conditions for nuclear fusion were met and the first light in the universe switched on. The fog began to clear once those first stars and galaxies ignited. Massive, extremely hot young stars and the energetic environment surrounding the first galaxies produce enormous quantities of ultraviolet radiation, energetic enough to strip electrons from neutral hydrogen atoms entirely, a process called ionization. Each newly formed star or galaxy carved out a growing bubble of ionized, transparent gas in the space immediately around it, exactly like a single floodlight burning back the fog in its own corner of the stadium. The bubble grew as more stars formed within it. Where two bubbles from neighboring galaxies expanded far enough to meet, they merged, the cleared regions joining into larger and larger patches of transparency. As more stars and galaxies formed across the universe, these bubbles grew and gradually merged with one another, until the neutral hydrogen fog that had once filled the entire cosmos was reduced to scattered, shrinking patches and finally disappeared almost entirely, leaving the universe transparent to ultraviolet light for the first time since the Dark Ages began. That is the theory. Confirming it actually happened required a specific observational technique, built around the most distant, brightest beacons available. Quasars, the extraordinarily luminous, energetic centers of early galaxies powered by supermassive black holes, bright enough to be detected at extreme redshifts, where ordinary galaxies remain too faint to resolve in detail. As light from a sufficiently distant quasar travels toward Earth, it may pass through neutral hydrogen gas still lingering along the way. Neutral hydrogen absorbs light very specifically, at and around the Lyman alpha wavelength covered 2 chapters earlier. If the quasar's light passes through a region still filled with that gas, the absorption leaves a wide, unmistakable gap in the observed spectrum, a trough carved out of the light by the time it arrives at Earth, redshifted according to how far it travelled. Astronomers call this the Gunn-Peterson trough, after the 2 scientists who first predicted its appearance. If the quasar's light instead passes only through already ionized transparent gas, no such trough appears. The absorption simply isn't there to leave a mark. That difference, trough or no trough, is the entire signature. By examining the spectra of quasars at a range of different redshifts, astronomers have been able to track exactly where those troughs start appearing and where they stop, mapping the transition from an opaque, fog-filled early universe to a transparent one quasar sightline at a time. The next generation of instruments is approaching the problem from an entirely different angle. Rather than inferring the presence of neutral hydrogen indirectly through what it blocks in a quasar's spectrum, radio telescopes are being built specifically to detect neutral hydrogen directly through a faint emission feature called the 21 centimeter line, a radio wavelength produced naturally by neutral hydrogen atoms, regardless of whether a bright quasar happens to sit usefully behind them. Projects including the Square Kilometre Array, an international radio observatory currently under construction across sites in Australia and South Africa, aim to use this signal to build a direct, 3-dimensional map of where neutral hydrogen still remained at each stage of reionization, rather than relying on scattered quasar sightlines alone. What this combined body of evidence firmly establishes is that reionization happened, and it happened within a defined and increasingly well-constrained window of cosmic time. The fog cleared. The universe became transparent. What remains actively debated is not whether that happened, but precisely which floodlights did the clearing. How much of the ionizing radiation came from the earliest ordinary star-forming galaxies, and how much may have come from energetic quasars and accreting black holes contributing alongside them. That question is what the next generation of radio telescopes is specifically being built to answer, and the universe, silent on the matter for over 13 billion years, is only now beginning to be heard. In 1965, two engineers at Bell Labs in New Jersey were trying to eliminate a persistent hiss of static from a large horn-shaped antenna originally built for satellite communication, and they could not make it go away. Arno Penzias and Robert Wilson had ruled out every conventional source of interference they could think of. They checked the antenna's wiring, tracing each connection methodically, looking for a fault that wasn't there. They checked the receiver itself, suspecting a flaw in the electronics that might be generating noise internally. They pointed the antenna at different parts of the sky and found the static remained constant, regardless of direction, regardless of time of day or season, which ruled out any local source on the ground and any astronomical object in a fixed position overhead. They even climbed inside the antenna structure itself and cleaned out what they described as a build-up of pigeon droppings, suspecting the birds nesting there might be the culprit. They removed the pigeons. They cleaned the surface. The faint hiss persisted at exactly the same low level no matter what they tried, a uniform background noise corresponding to a temperature of just under 3 degrees above absolute zero, present everywhere they pointed the antenna, with no apparent source anywhere in the sky, on the ground, or inside the instrument itself. What Penzias and Wilson had stumbled into, without initially realizing it, was not noise at all. It was light, the oldest light in the observable universe, arriving from every direction simultaneously because its source was not a single object somewhere in the sky, but the entire universe itself, at a moment in its infancy. The uniformity that had made it so frustrating to eliminate, its presence in every direction at exactly the same intensity, was not a property of a malfunctioning antenna. It was a property of the radiation itself. Working in close contact with a nearby team of theorists at Princeton who had independently predicted that exactly this kind of radiation should exist as a relic of the early universe, Penzias and Wilson realized their unexplained antenna noise was the cosmic microwave background, and the discovery, made entirely by accident while trying to fix a different problem, earned them the Nobel Prize in Physics in 1978. To understand what that radiation actually represents requires reaching back further into cosmic history than any chapter of this journey has gone so far, back beyond even the earliest galaxies detected by JWST and the reionization fog that surrounded them, to a period roughly 380,000 years after the Big Bang. Before that moment, the universe was an extremely hot, dense plasma, far too energetic for electrons and protons to combine into stable atoms. Any photon of light produced in that environment travelled only a tiny distance before colliding with a free electron and scattering off in a new direction, over and over, endlessly. The same way light entering a pane of heavily frosted glass scatters in every direction before it can pass through, never travelling in a clean straight line. The early universe was, in this specific sense, genuinely opaque. Light existed, but it could not travel freely. It was trapped, bouncing endlessly between charged particles in a dense hot fog that stretched in every direction without limit. As the universe expanded, it cooled. At roughly 380,000 years, the temperature dropped to approximately 3,000 Kelvin, cool enough, finally, for electrons to bind to protons and form stable neutral hydrogen atoms, the same neutral hydrogen that filled the cosmic dark ages described in the previous chapter. Astronomers call this transition recombination, or sometimes decoupling, since it marks the moment photons decoupled from matter and were finally free to travel in straight, uninterrupted lines. It is the precise moment the frosted glass turned clear. The light released at that exact instant has been travelling through the universe ever since. stretched dramatically by cosmic expansion over the following 13.8 billion years, from its original intensely hot wavelength down into the microwave range detected by Penzias and Wilson's antenna, a uniform glow filling every direction of the sky, the literal afterglow of the moment the universe became transparent. There is something worth dwelling on in that image before moving further. The light Penzias and Wilson detected with their horn antenna in New Jersey in 1965 had been travelling for over 13 billion years before it arrived. It left its source not from a single star or galaxy or any object that has ever been named, but from the entire visible sky simultaneously. At the moment the universe first allowed light to move freely, every point of that sky was, at that instant, glowing at the same temperature, releasing the same radiation in every direction. The universe was its own light source, and the afterglow of that moment is still arriving, still filling every direction, still detectable by any sufficiently sensitive instrument pointed anywhere in the sky. Once the nature of this radiation was understood, subsequent missions were built specifically to study it in far greater detail than a single fixed antenna ever could. NASA's Cosmic Background Explorer, COBE, launched in 1989, produced the first confirmed map of tiny variations in the CMB's temperature across the sky. To hold the scale of those variations, a typical household thermostat might register temperature differences of a single degree as significant. Laboratory-grade thermometers can resolve differences 100 times finer than that. The fluctuations COBE detected were finer still, by a further factor of roughly 1,000, amounting to differences of 1 part in 100,000, mere millionths of a degree layered across a background glow, measured in degrees above absolute zero. COBE's confirmation of those fluctuations earned its own Nobel Prize in 2006. Later missions pushed that precision even further. WMAP launched in 2001, and the European Space Agency's Planck satellite, launched in 2009, mapped those same temperature variations across the full sky with steadily increasing resolution, revealing not random static but a structured pattern of slightly warmer and slightly cooler patches. Those patches represent tiny differences in the density of matter at the moment of recombination, the overdense regions mentioned in the previous chapter as the seeds of the first stars and galaxies. It was precisely those small density differences, amplified over hundreds of millions of years by gravity, that eventually collapsed into everything this journey has described from the Milky Way outward. The faint fluctuations mapped by COBE, WMAP, and Planck are not a detail. They are the origin of all subsequent structure in the observable universe. The cosmic microwave background represents something this journey has not encountered at any previous threshold. It is not simply the furthest light current instruments happen to have detected. It is the furthest light any instrument, of any kind, could ever detect using electromagnetic radiation, because there is no earlier light to find. Before recombination, the universe was opaque, scattering every photon before it could travel any meaningful distance. The cosmic microwave background is not a horizon that future telescopes might someday push past. It is a wall, and just beyond it, the universe holds its oldest secrets in the only place light cannot reach. Walk into a concert hall long after the last performance, and the room is not silent in the way an empty field is silent. The walls still hold something. The way sound decays off the plaster, the way certain frequencies linger in the high corners, the way the space itself rings faintly when disturbed, all of it carries information about what happened here. Precisely enough that an acoustician who never attended the performance could reconstruct, with real precision, how a particular note would have rung out the night it was first played. Physicists working before the cosmic microwave background do something similar. No telescope will ever see past it. But the wall itself, and everything that survived on this side of it, still carries the signature of what came before. This chapter covers 2 such reconstructions. They sit at very different levels of confidence, and it is worth knowing which is which before either one is described. The first concerns Big Bang nucleosynthesis, the brief period beginning roughly 1 second after the Big Bang and largely complete within about 20 minutes. during which the universe was hot and dense enough for protons and neutrons to fuse directly into the lightest atomic nuclei. This was not a gradual stellar process like the fusion happening inside stars today. It was a narrow, universe-wide window, open only while temperatures remained in the precise range fusion requires, and closing permanently once expansion cooled the universe below that threshold. In those 20 minutes, the universe ran through a process that stars spend millions of years completing, forging the lightest elements in a single brief window that would never open again. The theory makes a sharp, falsifiable prediction. It specifies almost exactly what ratio of hydrogen to helium should have resulted from that brief window, roughly 75% hydrogen to 25% helium by mass, with only trace amounts of lithium and other light elements alongside them. The precision of that prediction is worth pausing on. The theory does not say approximately 3/4 hydrogen. It specifies the ratio to within a fraction of a percent, a figure that emerges from the physics of nuclear reactions at specific temperatures and densities, calculated from first principles without any free parameters adjusted to match the observation. That prediction has been tested directly, not by observing the event itself, but by measuring the actual chemical composition of the oldest, most pristine gas clouds astronomers can find. Regions that have remained largely unprocessed by subsequent generations of stars, which manufacture heavier elements and would otherwise contaminate the primordial ratio. Spectroscopic analysis of these ancient clouds, using the same absorption line techniques developed earlier in this journey, consistently returns a hydrogen to helium ratio matching the nucleosynthesis prediction with remarkable precision. The same neutral hydrogen that filled the cosmic dark ages, that blocked the light of the first quasars, that Penzias and Wilson's antenna was already bathed in without knowing it, turns out to exist in precisely the proportion a theory of the first 20 minutes predicted it should. This agreement is one of the strongest pieces of evidence supporting the Big Bang model as a whole. A theory predicted a precise number. Independent observation of clouds the theory was never built to describe directly returned that same number. Nucleosynthesis is treated as essentially confirmed physics, not speculation. That is the first reconstruction, and it stands on solid ground. The second does not yet. Pushing earlier still, into the first fraction of the first second, the evidence becomes considerably less direct, and the central idea governing this era, inflation, carries a correspondingly different evidentiary status. To climb toward how brief the interval inflation is proposed to have occupied, begin with a single second and divide it into 1,000 milliseconds. Divide each millisecond into 1,000 microseconds. Divide each microsecond into 1,000 nanoseconds. Divide each nanosecond into 1,000 picoseconds. Continue that same thousandfold division many more times over, and even then the resulting interval still falls dramatically short of the window inflation is proposed to have filled. It is a span so far outside ordinary experience that no familiar unit of time comes within reach of it. The entire history of recorded human civilization, every empire, every war, every book, compressed into a single second, would still be an eternity compared to the interval inflation is proposed to have occupied. Inflation proposes that within that interval, the universe underwent an exponential, faster-than-light expansion of space itself, ballooning by a vast factor before settling into the steadier expansion that has continued ever since. It was proposed in the early 1980s, independently developed by physicists, including Alan Guth, in part because it elegantly solves several puzzles the standard Big Bang model struggled to explain on its own. It accounts for why the observable universe appears so close to spatially flat, meaning that light travels through it in straight lines rather than curving back on itself the way it would in a universe with significant overall curvature. It accounts for why regions of the sky too far apart to have ever exchanged light still display nearly identical cosmic microwave background temperatures, a uniformity that the standard Big Bang model without inflation cannot explain, since those regions could never have been in contact long enough to reach the same temperature through any ordinary physical process. Inflation explains both puzzles in a single step by proposing that the entire observable universe expanded from a region so small that it had time to reach thermal equilibrium before inflation stretched it to its current enormous size. These successes are real, and they are the reason inflation remains the leading theoretical framework for this earliest era. But unlike nucleosynthesis, inflation has not been directly confirmed by any matching observational signature of comparable strength. It explains. It has not yet been proven the way a falsified or confirmed prediction proves something. Physicists do have a specific target they believe could close that gap. It is called B-mode polarization, a subtle twisting in the orientation of the cosmic microwave background's light. If detected at the right scale and pattern, it would represent the imprint of gravitational waves generated specifically by inflation itself, a signature no other known process could easily produce. Several experiments, including the BICEP collaboration working from the South Pole, have searched for this pattern. An initial claimed detection in 2014 was later found to be explained by foreground dust within our own galaxy, rather than a genuine primordial signal. The search continues, using increasingly sensitive instruments, and the answer it returns will either confirm the leading theory of the universe's first moment or force a significant revision of it. This leaves the earliest moments of cosmic history in a genuinely two-tiered evidentiary state. Nucleosynthesis stands on solid, independently confirmed ground. Inflation remains the leading explanation for several otherwise unexplained features of the universe, but it remains unconfirmed. And beyond both of these, beyond the observable horizon, this entire journey has been measuring outward from Earth. The question of what actually exists, whether simply more universe extending beyond what light has had time to reach, or something structurally different, remains honestly and necessarily open. The wall is real. What lies on the other side of it is not yet a question physics can properly answer, only one it can clearly see. Climb to the crow's nest of a ship, gain a few dozen feet of altitude, and the horizon visibly recedes, not because the sea has grown larger, but because height alone reveals more of what was already there. The observable universe's horizon grows the same way, gaining roughly 1 light-year of additional reach for every year that passes, not through any act of exploration, but simply because there has been 1 more year for light to complete its journey to Earth. That principle, introduced at the very start of this journey, is worth holding firmly now. Every threshold crossed since has been a different kind of edge, and naming them in sequence reveals something about the structure of knowledge itself, not just the structure of the cosmos. Taken together, these thresholds describe a universe with specific, measured properties. It is old, 13.8 billion years by multiple independent dating methods converging on the same figure. It is expanding, a fact established by Hubble nearly a century ago and refined, if not yet fully agreed upon, ever since. And according to the same Planck satellite data that mapped the cosmic microwave background's fine temperature structure, it is composed overwhelmingly of material that emits no light at all. Ordinary matter, the atoms making up planets, stars, and every living thing, accounts for only about 5% of the universe's total content. The remainder splits between dark matter, an unseen substance inferred from its gravitational effects on galaxies and clusters throughout this journey, and dark energy, the still poorly understood force driving the universe's expansion to accelerate rather than slow under its own gravity, a property neither directly observed nor yet explained at a fundamental physical level. These are not small uncertainties at the margins of an otherwise complete picture. Dark matter and dark energy together account for roughly 95% of everything the universe contains, and neither one has been directly detected in a laboratory or explained from first principles. The universe, as currently understood, is mostly made of things we cannot see and do not yet fully understand. The first edges were physical and mechanical, reached through direct spacecraft measurement. The Kuiper Belt, that disk of icy debris from roughly 30 to 50 astronomical units out, was confirmed through direct imaging once New Horizons reached Pluto and Arrokoth in turn. The heliopause, the true edge of the Sun's influence near 120 astronomical units, was confirmed through Voyager 1's plasma density jump. a 20-fold increase in electron density that took a delayed second measurement to fully verify. These are settled findings, built on spacecraft that physically crossed the thresholds in question and reported back directly. They are also, in the context of this entire journey, almost incomprehensibly close. The heliopause, the furthest point any human-made object has ever reached, sits at 120 astronomical units from the Sunday. The observable universe extends to roughly 46 billion light-years in every direction. The distance Voyager has travelled, the entirety of humanity's physical reach into space, represents a fraction of the total so small it does not register on any scale this journey has used. The next edges were gravitational rather than physical, measured indirectly through motion rather than direct crossing. The Milky Way's 100,000 light-year disk and the Sun's position within it were mapped through Cepheid variables and confirmed with extraordinary precision by Gaia's parallax measurements of over 1 billion stars. Andromeda's approach toward the Milky Way, measured through spectroscopic blueshift, set the stage for a 4.5 billion-year collision course no longer seriously disputed. And Laniakea, the 500 million light-year supercluster containing both galaxies, was identified not by sight, but by tracing the peculiar velocities of tens of thousands of galaxies back to a shared gravitational basin, work that simultaneously revealed an unresolved thread still being investigated. The Great Attractor, whose full nature and whether anything larger still draws Laniakea toward it, remains genuinely open. Beyond gravity's organizing reach, the edges became observational rather than structural, measured through redshift rather than direct motion. The Hubble Flow carries the cosmic web's filaments and voids outward, at a rate still genuinely contested between two careful independent measurement camps. The distance ladder figure near 73 km per second per megaparsec, and the cosmic microwave background derived figure near 67. A 5 sigma disagreement that remains unresolved despite years of refinement on both sides. Deep field observations from Hubble and James Webb pushed that same redshift toolkit to its practical limit, finding galaxies beyond z=14 that appear more massive and structured than current formation models predicted, and active tension still being worked through. And reionization, the clearing of the universe's neutral hydrogen fog between roughly 150 million and 1 billion years after the Big Bang, stands on firmer ground, confirmed through Gunn-Peterson trough measurements in quasar spectra, even while the precise mix of sources responsible for that clearing remains debated. Then came the final edge in light itself, the cosmic microwave background, radiation released at recombination roughly 380,000 years after the Big Bang, discovered by accident as unexplained antenna noise, and later mapped with extraordinary precision by Kobe, Womap, and Planck. This is not simply the most distant light yet detected. It is the most distant light any instrument could ever detect, a literal wall built from the universe's own early opacity. Beyond it lies only inference, nucleosynthesis confirmed through matching light element ratios, inflation still awaiting the B-mode polarization signature that would move it from leading theory to confirmed physics, and a question about what exists beyond the observable horizon altogether that current physics can see clearly but not yet answer. What should be carried forward from this journey is not a single settled picture, but a clear sense of where the settled ground actually ends. The heliopause crossing, the Milky Way's scale, Andromeda's trajectory, reionization's timing, recombination itself. These stand on solid, independently confirmed measurement. The Hubble tension, the Great Attractor's full extent, the precise drivers of early galaxy formation, the nature of dark energy, and inflation's still unconfirmed signature remain open questions, actively investigated rather than resolved. The line between those two categories, between what is known and what is not yet known, is itself one of the most precisely drawn boundaries in all of science. It is not a vague frontier, it is a specific list of measurements, each one with a named uncertainty, each one being worked on by named people using named instruments. in observatories and laboratories that exist right now. Less than a century ago, astronomers did not know galaxies beyond our own existed at all. Voyager had not yet measured the Sun's true edge. No one had identified Laniakea, or detected a single galaxy beyond z=10, or resolved a single fluctuation in the cosmic microwave background. Each of those things is now known, measured, confirmed. The pace at which that list has grown is itself one of the more remarkable features of the last 100 years of human knowledge, a sustained expansion of the known that has moved outward in every direction simultaneously, from the solar system's edge to the structure of the cosmic web to the temperature fluctuations imprinted on the oldest light in the universe. And the horizon itself keeps expanding, 1 light year for every year that passes, not because anything is being explored further, but simply because more time will have passed for more light to arrive. Somewhere out there, beyond the current edge of what can be seen, light that left its source before any of these chapters began is still travelling toward us. It has been travelling the entire time this journey has taken. It will arrive, eventually, adding one more layer to the observable universe, one more data point in the long, patient work of understanding where all of this came from and how far it goes. What lies just beyond the current edge of knowledge is not darkness. It is the next thing waiting to be seen.